Hi everyone. In the last video we talked about curl and divergence. So in this video it's time to get to Green's theorem. There are two different versions of Green's theorem in this section. The first one is Green's theorem for circulation and curl. Before we get to the actual theorem though, let's look at a couple concepts that we're going to need and actually revisit some definitions we already know. So we need C to be a simple closed curve. Remember, simple means the curve doesn't intersect itself, and closed means that it doesn't have distinct endpoints. It's some kind of loop. We say C has a positive orientation if it's traveled counterclockwise or traversed counterclockwise. Now we talked about this a little bit when we talked about flux integrals, which is also going to come up in this section. All right, so here's an example. I have this closed curve, and it's going around counterclockwise, and I've filled in the region and called it D, but right now let's just focus on C. So this definition is going to work most of the time when we talk about positive orientations, but a better way to think of it is this analogy of imagine that you're walking along the curve, and if the interior of the curve is to your left, that's a positive orientation. Or you could think of here some path along a pond, the outside of a pond. If the pond is on your left as you're walking, that's a positive orientation. Okay, here's an example of a negative orientation where we're going around the curve clockwise. All right. We also need this region enclosed by the curve to be simply connected. Now remember, simply connected for two dimensions, which is what we're going to deal with Green's theorem. Simply connected just means that the region doesn't have any holes in it. And so if we just fill in the interior of a curve, that should be true if we have a simple closed curve. Okay, now Green's theorem, this first form of Green's theorem, what it does is it says that the work done by a vector field along a curve is the same as the kth component of curl inside of the region. And so here it is, Green's theorem, the circulation curl case. Much of the hypotheses we've already discussed. I'll go over them again. So let C be positively oriented. You go around it counterclockwise. Piecewise smooth. So smooth, again, we've talked about this before. It means it has a parameterization that you can take a derivative of, and the derivative is non-zero everywhere. Piecewise just means it can be broken into smooth pieces. So it might have some points where it's not differentiable, but the pieces of the curve connected at that point should be smooth. Okay, and so it's positively oriented, piecewise smooth, simple closed curve in the xy plane, and let D be the region bounded by C. If it's bounded by a simple closed curve, it should be simply connected. Now, if P and Q, these are going to be components of a two-dimensional vector field. If they have continuous partial derivatives on an open region that contains D, this is a hypothesis that we need, so you can just think of going outside of the curve a little bit and taking an open region there. As long as they're continuous outside of the region just a little bit, then here's the important part, this formula holds. So this is the line integral over the closed curve, p dx plus q dy. This is equal to the double integral of this kth component of curl inside the region. All right, so this partial derivative of q with respect to x minus the partial derivative of p with respect to y. Now we can simplify this notation a little bit, or just write it a different way. If you remember what we used when we talked about flux integrals, if I have this integral symbol with a circle and an arrow pointing, this just means the line integral over a positively oriented closed curve. And so we can rewrite Green's theorem in this way. Instead of in terms of P and Q, I can just write the integral over a positively oriented closed curve, that's what this symbol means, of f dot dr. So those are the line integrals we talked about in section 16.2 and 16.3. This is equal to the curl of f dot k, so that gives you just the kth component of curl inside the region. All right, so that's that partial derivative of q with respect to x minus the partial derivative of p with respect to y. If f is conservative, what happens? Well, we know that if f is conservative, then we can use the fundamental theorem of line integrals, and over a closed curve, it should be zero. This integral should be zero. We also know that for a conservative vector field, that the curl is 0. So this integral is 0. So Green's theorem, we've just basically verified it if f is conservative, but it also works for other vector fields. And there are some exercises in the textbook that ask you to verify it. I'm not going to verify it here. We're just going to use Green's theorem to do a couple of examples. Okay, so the first example, use Green's theorem to evaluate this line integral. So we have the integral of y cubed dx plus x cubed plus 3xy squared dy, where c is the path starting at the origin and then going to the point 1, 1 along y equals x cubed, and then back to the origin along y equals x. So let's look at our path first. I'm starting at the origin, and let's pretend that this curve is y equals x cubed. I'm moving along this curve y equals x cubed till I get to the point 1, 1, and then I go straight back to the origin along the line y equals x. So this is a closed curve. Right? I'm ending where I started. It's simple. It doesn't intersect itself, except at the starting point and ending point, which is fine. It's still a loop. It's piecewise smooth. X cubed is smooth. X is smooth. And then we just have these 2 points where it's not differentiable, but that's okay. We're allowed to have that. And it's positively oriented. I'm going around this curve counterclockwise. So it fulfills all the hypotheses of Green's theorem. We can use Green's theorem, which means instead of computing this line integral, which we would have to actually set up 2 line integrals, right? Because I have 2 different pieces. They'd have separate parameterizations. Instead of doing that, I can just solve a single double integral. So what's my double integral going to be? Let's identify P and Q. P is y cubed. Q is x cubed plus 3xy squared. When I set up this double integral, I need the partial derivative of q with respect to x and the partial derivative of p with respect to y. So if I take those partial derivatives, I get 3x squared plus 3y squared for partial derivative of q with respect to x, and 3y squared is the partial derivative of p with respect to y. So I set up this double integral. Green's theorem says it's equal to this line integral. That's what I want to find. But this line integral is equal to the double integral of 3x squared plus 3y squared, which was this partial derivative, minus 3y squared, which was this partial derivative. Well, the 3y squares cancel out, and I'm just left taking the double integral of 3x squared over this domain. So this is what I want to find now. This is going to be easier to find than this line integral, which again, I'd have to set up 2 separate integrals. So now what's missing? I need bounds of integration for d. So now I need to go back to this region and figure out, okay, how do I want to set up my bounds? Do I want to integrate with respect to y first? Do I want to integrate with respect to x first? Well, since these are already solved for y, well, I guess this you could think of solved for y or x. It doesn't matter. But since y equals x cubed is solved for y, let's go ahead and integrate with respect to y first. So I think about moving in this small region here vertically. The bottom curve is always x cubed, and the top curve is x. So I'm going from x cubed to x in a vertical manner through this region. So this region can be described as all the points that are between x, where y is between x cubed and x goes from 0 to 1. So those are going to be my bounds. So I set up my integral. Once again, this is the line integral that we wanted to find. This is equal to the double integral of 3x squared, where when I'm integrating in y from x cubed to x, and I'm integrating in x from 0 to 1. So I go ahead and integrate with respect to y. I get 3x squared y from x cubed to x. I plug in my bounds. That gives me 3x cubed minus 3x to the 5th. And now I'm ready to integrate with respect to x. That gives me 3/4 x to the 4th minus 1/2 x to the 6th from 0 to 1, which is 3/4 minus 1/2 minus 0 plus 0. And 3/4 minus 1/2 is 1/4. And that's my answer. Now you can go back and compute the line integral. And it's probably going to take a lot more work. Not too much though. I mean, it's doable. It's something that can be done. You should get that the answer is 1/4. All right, let's look at another example. So evaluate this line integral. Here we're already told ahead of time with this symbol. That's this closed curve with a positive orientation. We want to integrate arctangent of x plus y squared dx and e to the y minus x squared dy, where c is the semi-annulus as shown in the graph. Well, here's the graph. You can see the pieces of this curve has a positive orientation. It's piecewise smooth. There are 4 pieces. There's a segment on the x-axis, this semicircle of radius 3, this piece on the x-axis, and then a semicircle of radius 1. So if I want to evaluate this line integral, I actually want to compute the line integral, I'm going to need 4 line integrals, one for each piece of that curve. So instead I'm going to use Green's theorem and compute a double integral. But we saw in the last section that we talked about, 15.4, if I have a region like this that I want to integrate over, and I use x and y coordinates, I'm going to need 3 double integrals to represent the integral over this region. So 3 is less than 4, so that's still better, but we can do even better if I switch to polar coordinates. If I switch to polar coordinates, I can represent this region with 1 double integral, and that's much easier. Another reason we should do the double integral instead of the line integral is look what happens when we take the derivatives we need. So p was arctangent of x plus y squared. If I take a derivative with respect to y, that just becomes 2y. Much easier to deal with. I don't want to have to integrate arctangent, and so if I do the double integral, I don't have to. And with q, I get rid of the exponential. So I take a derivative with respect to x, I get negative 2x. Okay, now my bounds in polar coordinates, r goes from 1 to 3, because those are the radii of the circles I'm going between, and theta goes from 0 to pi, because I only have the top half of this annulus, if I think of the double integral. So now I set up this double integral. I think we're done with this sheet. So this line integral that I was asked to find is equal to the double integral of negative 2x, which was partial derivative of q with respect to x, minus 2y. 2y was the partial derivative of p with respect to y. But now I need to convert this to polar coordinates. So I can put in my bounds for theta and r. X becomes r cosine theta, y becomes r sine theta, and don't forget to multiply by r. Remember, when we switch to polar coordinates, we have to multiply by r, because dA is actually r dr d theta. Okay, now this integral becomes even better because I can factor a negative 2 out front. I can think and factor this r to the right, and I have something that's separable. I have cosine, if I factor a negative 2 out, and I factor an r out, I have cosine theta plus sine theta times r squared. So I can separate this integral. Remember, you don't have to do that, but in this case, we're allowed to. And so instead of a double integral, I have a product of 2 single integrals. I have negative 2 times the integral in theta from 0 to pi of cosine plus sine times the integral in r from 1 to 3 of r squared. So now I just integrate. I integrate cosine to get sine. I integrate sine to get negative cosine. That's evaluated from 0 to pi. R squared integrates to 1/3 r cubed. I evaluate from 1 to 3. And from here, it's just a matter of plugging these numbers in and doing some arithmetic, which I will leave you to verify. All the steps are there, but the answer is negative 104/3. All right, so we're going to stop here. In the next video, we'll do a couple more examples of using Green's theorem and talk about the second version of Green's theorem, which involves flux.